Hi, and welcome back to my YouTube channel on David Structure Hub, a place where you learn, build, and innovate. In this channel, we break down complex civil engineering concepts, solve past questions step by step, and also share practical skills for students, trainers, and future engineers. So let's build a knowledge that lasts. In today's lesson, I want to tackle a problem from timber design to BS 5268. And before then, let me remind you something. For those who have not subscribed to this channel, please do so and hit that notification bell so that you may be the first person to be notified when I upload a video. So stay tuned up to the end. The question is on the board and it reads, a timber joist 100 by 250 millimeter of effective span 4 meters at 500 millimeter center to center bears on a 200 millimeter wall. Using the data given, determine the permissible load per unit area which can safely applied on the wall, given that dead load is equal to 1 kilonewton per meter square, strength class is equal to C16, permissible deflection 0.03 times span. Assume medium term loading. So solution. So the first thing to do is to determine the total loading. And as you can see, we have been given a dead load of 1 kilonewton per meter square. So this is a permanent load. Dead load is a permanent load, and we have not been given an imposed load. So what we are looking for is imposed load in this question. So you will start by determining the total loading. So total loading. Since you have not been given an imposed load, we will say let imposed load equal to QK. That is our imposed load. So the total loading will be imposed load plus the dead load. So it will be 1 plus QK. And remember, this is in kilonewton per meter square. So that is our total loading. So load per joist, load per joist. In other words, we want to reduce this loading, which is total loading, from kilonewton per meter square to kilonewton per meter. So you will take our total loading, which is 1 plus QK multiplied by the spacing, which is 500 millimeter center to center. So times 500, then you divide by 1,000 because we want to change this 500 millimeter center to center to meters center to center. So if you multiply, you will get, so this one will be 1 plus QK multiplied by 0.5. You can open the bracket. So you will have 0.5 plus 0.5 QK. So this is our total loading. So if we can draw our beam, our joist, not beam, the effective length is 4 meters, and this is our imposed load, which is 0.5 plus 0.5 qk, kilonewton per meter. That is our total loading on this joist. Then after that, we will calculate our maximum moment. So our maximum moment is equal to WL square over 8. So this one will be M max. Our W is this load, total loading on the beam, which is 0.5 plus 0.5 qk times L. L is 4 meter, so square over 8. So that one will be 0.5 times 4 square divided by 8. So this is 1 plus qk, and this is in kilonewton meter. After doing so, we will again calculate our reaction or a shear force. So the next thing is reaction, stock shear force, which is V. So our reaction will be V is equal to WL over 2. Because it is a UDL, you will change it to point load by multiplying the length, which is 4, and then you divide by 2. So it will be, our loading is 0.5 plus 0.5 qk times our length is 4 over 2. So V is equal to, you can punch your calculator, 0.5 times 4 divided by 2. So that is 1 plus qk. So this is in kilo Newton. After doing so, our next thing to do is to proceed to modification factors. Modification factors. So I will rub here to create space for more calculation. Modification factors. So we'll start by K3. So in the question, you have been told we have been told to assume medium-term loading. So our K3 for medium-term loading is 1.25. 1.25. After that, we will proceed to K7. So K7. So our K7, it will be 300 over H raised power 0.11. It is because our H is equal to 250 millimeter, which is above 75 millimeter, but below 300 millimeter. So K7, therefore, or which imply K7 is equal to 300 over 250 raised power 0.11. So K7, which is equal to 300 raised power 0.11. So that is 1.02. 1.02. So that is K7. And then K8 is equal to 1.1. 1.10. The reason is the spacing is below 610 millimeters center to center. So that is the reason. If the spacing will be above 610 millimeters center to center, then we will have choose another factor, which is 1.0. After this, we will move to grade stresses. And this one will be obtained from strength class C16. So we have bending parallel to grain, and then compression perpendicular to grain, and then you have shear parallel to grain, and then you have E mean. So E mean also will be obtained from grade stresses strength class C16. So I will show you the table, the table of grade stresses. So this is the table, and this is how you obtain the value. During your exam, you will be provided with this table, so you should not worry about the table. So as you can see, we have strength class 16. You can check or see the movement of my cursor. So under that class 16, you will move to bending parallel to grain, which is the first column, and obtain that value. So it is 5.3 Newton per millimeter square. And you will write it here, 5.3 Newton per millimeter square. You will proceed to compression perpendicular to grain. The same strength class, proceed to compression. We have two values, 2.2 and 1.7. So you'll take the lower value, which is 1.7, and write it here, 1.7 Newton per millimeter square. You'll proceed to shear parallel to grain using the same strength class. So shear parallel to grain, that is 0.67. So 0.67 Newton per millimeter square. And then we'll proceed to E mean. Using the same strength class, our E mean is 8800 Newton per millimeter square. So that is 88 Newton per millimeter square. After that, you'll proceed to permissible stresses. So permissible stresses, so we will start by bending parallel to grain. Bending parallel to grain. So the permissible stresses for bending parallel to grain will be modification factor K3 times K7 times K8 times bending times grade stress bending parallel to grain. So that is 5.3. So our K3 is 1.25 times K7. K7 is 1.02 times K8, 1.10 times 5.3. So remember, K3, it modify all the grade stresses. Also K8, but K7, it only modify bending parallel to grain. Then you punch your calculator. 1.25 times 1.02 times 1.10 times 5.3. So that is 7.43 Newton per millimeter square. So that is bending parallel to grain. We proceed to compression perpendicular to grain. So compression perpendicular to grain. So we'll take K3 times K8 times 1.7. So this one is equal to 1.25 times 1.10 times 1.7. Then you punch your calculator. 1.25 times 1.10 times 1.7. So that is 2.34 Newton per millimeter square. And then we proceed to the last one, which is shear parallel to grain. Again, let me clear here for more calculation. So the last one is shear parallel to grain. So that one will be K3 times K8 times 0.67. Our K3 is 1.25 times 1.10 times 0.67. So that is 0.92 Newton per millimeter square. And then after there, we proceed to design consideration. So the first design consideration is bending. Design consideration. Bending. So we know that Z is equal to M over F. So this is the formula for bending. So Z is the section modulus, and M is the moment, and F is the permissible stress in bending. So Z, but Z is equal to BD square over 6. And remember, our section is 100 by 250 millimeter. So this is our section. So it means Z is equal to, so this is our B, and this is our D, 100 times 250 square over 6. Then you punch your calculator. 100 times 250 square divided by 6. So that is 1.042 times 10 raised to power 6 millimeter to power 3. So after doing so, we know that our maximum moment is 1 M max is equal to 1 plus QK kilonewton meter. So if we make here M the subject of the formula, will end up having, so Z is equal to M over F. So make M the subject of the formula, which imply M is equal to Z times F. You cross multiply. So our F here is the permissible stress in bending, which is 7.43. So M is equal to, our Z is 1.042 times 10 raised to power 6, then times F. Our F is 7.43 Yeah, like that. So remember, this is in Newton per millimeter square, and this is in millimeter cubic. So you will divide by 10 raised power 6 so that your answer will be in kilonewton meter. So the answer will be equals to 1.042 times 7.43. So that is 7.74. 7.74 kilonewton meter. Remember, our first moment, maximum moment, was 1 plus qk. So we want to find the value of qk. So you will equate this to this expression. So you will end up having 1 plus qk is equal to 7.74, which means qk is equal to 7.74 minus 1, which imply qk is equal to 6.74 kilonewton per meter. So that is our qk, but not our answer. We'll do the same for shear, for bearing, and for deflection, so that we may get the least value of all the values for design consideration, and that value will be our permissible stress. So let's continue. Again, let me rub here to create more space for calculation. So we proceed to design consideration number 2. So number 1 was bending, and number 2 is shear. So number 2 is shear. We know that Q shear is equal to 1.5 V over BD. So we can make this V the subject of the formula. So our V, which imply V is equal to over 1, then you cross multiply. So this times this will be Q in shear times BD over 1.5. So this Q in shear is the permissible stress in shear. So V is equal to the permissible stress in shear is 0.92 times B is 100 times D is 250 over 1.5. Then you punch your calculator. So 0.92 times 100 times 250 over 1.5. So the answer is 15,333.33. And remember this answer is in Newton. So you will divide by 1,000 to have your answer in kilonewton. So divide by 1,000. So that is 15.33 kilonewton. And remember, our first V, our V from the beginning was 1 point. So our V was 1 plus QK. So this was in kilonewton. So you will equate this expression to this value to find the QK. So 1 plus QK is equal to 15.33, which imply QK is equal to 15.33 minus 1. So QK is equal to 14.33 kilonewton. That is consideration number 2. We proceed to consideration number 3. So consideration number 3 is bearing. We know that Q bearing, the capital Q, is equal to V over Bx, where x is the bearing distance. So this is the bearing distance. Remember, in our question, we were told our wall is 200 millimeter. So the bearing distance will be a half of that wall, which will be 100. So x is equal to 200 over 2, which is equal to 100 millimeter. So make V the subject of the formula. So V is equal to, you cross multiply Q bearing times Bx, which is equal to, Q bearing is the permissible compressive stress, which is 2.34 times 100 times 100. So our B is 100. Let me rub here also. Then you can punch your calculator. 2.34 times 100 times 100. So that is V is equal to 234. This is in Newton. Then you divide by 1,000. to get your answer in kilonewton, divide by 1,000, which imply V is equal to 23 23.4 kilonewton, like that. Again, remember, our V is 1 plus small qk. So we are interested in this small qk. So you will compare this expression and V. So 1 plus qk is equal to 23.4. So qk is equal to 23.4 minus 1. So qk is equal to 22.4 kilonewton. We are going to proceed to design consideration number 3. So number 3 is deflection. So permissible deflection is equal to 0.003 times span. So this one is equal to 0.003 times 4,000. Our span was 4 meters, so you convert it from meter to millimeter. So you'll multiply 4 by 1,000 and you'll get 4,000. So this is 12 millimeter. That is our permissible deflection. We proceed to induced deflection. So this one is equal to 5 WL power 4 over 384 EI plus 12 WL square over 5 AE. So we can calculate the value of A and the value of I. So I is equal to BD cubed over 12. So our section was 100 by 250. So our B is 100 and our D is 250 over 12. And then you punch your calculator. So the answer is 130.21 times 10 raised to power 6 millimeter to power 4. Then area, length times width. So this one will be 100 times 250, which is equal to 25,000 millimeter square. So let me clear here. So we will use this formula, this one, and not this. The reason is this one is the deflection in bending, and this one is deflection in shear. So deflection in bending is far much greater than deflection in shear. So you can use this one instead of combining the whole of this. So use only deflection in bending. So we'll have 12, which is our permissible deflection, and then you equate to 5 WL power 4 over 384 EI. So 12 is equal to 5 times our W. We don't know our W, so our W is unknown. So W times length, that is 4 meters converted to millimeter, 4000 S per 4 over 384 times E. E is 8800 times I. I is 130.21 times 10 to the power 6. So it means 12 is equal to 2.91 W. If you punch your calculator, you will get 2.91 W. And then you divide both sides by 2.91. Which imply W is equal to 4.12 kilonewton per meter. So total design load is 1 plus QK. So this was in kilonewton per meter square. And then load per joist was 0.5 plus 0.5 QK. So this was in kilonewton per meter from our beginning of this question. So you'll compare this and 4.2 to get the value of QK. So this one will be 0.5 plus 0.5 QK is equal to 4.12. So if this crosses to the other side, it will be negative. So 0.5 QK is equal to 4.12 minus 0.5. So 0.5 QK is equal to, then you punch your calculator, you will get 3.62. Divide both sides by 0.5 by 0.5. So which imply QK is equal to 7.24 kilonewton per meter square. Therefore, the safe load that can be safely applied on the joist is 7.24 kilonewton per meter square, because it's the least. Is the least of the calculated values. So that is our permissible load that can be applied on the joist 7.24. So that marks the end of that question.